Introduce first Dr. Mutlu Ozdogan. He is an associate professor at the Department of Forest and Wildlife Ecology and Nelson Institute for the Environmental Studies from University of Wisconsin-Madison. Yeah, he has a doctorate in physical geography and remote sensing from Boston University. He has extensive research experience on varied fields ranging from geology, physical geography, environmental, remote sensing. Yeah, today he will talk about applications of remote sensing, a world tour. Yeah, this is all about Dr. Butler. Now he is giving a presentation.
Hi, everybody. Thank you so much for being here. Thank you for your time. I always wanted to visit ICRISAT, so I guess this was the time for me to do it. Again, I appreciate your time. Uh, as Murali said, I'm a trained geographer, and I studied with Curtis Woodcock at Boston University, who is more of a Landsat expert. So most of the data sets that I use are Landsat, in particular applications to agricultural problems. So today I'm going to try to talk about sort of three applications of remote sensing for agriculture in three different locations, and hence the word world tour, although it's not covering the entire world yet, but hopefully we'll get there soon. So let me start by doing this. So we know that there are a lot of sort of local to global challenges. We know there is increased competition, declining profit margins, there's environmental degradation associated with agriculture, resource constraints, regulatory oversight, at least in the US, and then the big question of feeding the world's population, climate change, et cetera, et cetera. I think we can add a lot more there. So what that wants us to do is to require us to produce more per field with fewer inputs at lower cost and with less impacts on resources. I think all of us are trying to get over here. And what I'm going to try to do is to present some research results to show that can we use remote sensing to get at some of these issues. We want to know a lot of things, right? We want to know crop yields, we want to know crop type, condition, residue, disease, pest, etc. These are the variables that we're very much interested in. And remote sensing may or may not be able to give us some of these variables. Some of these variables are easy to get from remote sensing, and some of them are very difficult to get from remote sensing. There are a lot of challenges, and I'm going to talk about those challenges in a second. But I'd like to, while showing these variables, I'd also like to do this. Not only do we want those variables, but the timing of those variables also matters. Some of those variables, we want to know them early on, such as disease and pests, so that we can do something about them during the growing season. When it comes to yield, for example, you really don't, unless it's an economic benefit, you really don't want to know the yield, as a yield is an integrated variable at the end of the season. So it's not necessarily a very early variable unless you can control it through disease or nutrient application. So there's this sort of temporal component to this early late. And good thing about remote sensing is that it gives us that some of the temporal variable. Not only that, but the spatial variability and spatial sort of detail of the information also matters. There are certain variables that you want to know in every part of the field in a sort of differential manner. The northeast corner of the field, you want to know northeast corner of the field better than the southeast corner of the field. There are other variables, the spatial resolution or spatial location doesn't really matter, such as the yield that you might be getting from your field. So there is this sort of temporal and spatial component that I'd like to talk about when it comes to those variables. And there's this idea of information to action cycle, right? So this is where remote sensing comes in. It's just a data collection platform. Then we take those data and then analyze them and come up with some decisions. And then hopefully those decisions lead to some application, and then the cycle begins again. And I would like to argue that remote sensing has been pretty good at data collection, and we've been, I think, very good at analysis for the last 30, 40 years. But we have not been very good at breaking this barrier over here. I am pretty much yet to see sort of applications of remote sensing that tells me that I have this great observation capability and great analytical capability, and I'm making better decisions because of remote sensing. Unfortunately, I'm a remote sensing expert, that's my job security, but I'm sad to say that we haven't broken that cycle. And hopefully we can get there with new tools and new data sets. And if you're not making better decisions over here, you're not necessarily making better decisions in terms of application. So where does remote sensing fit into all this? Again, as I said, remote sensing fits into sort of this data collection analytical part, but not so much in the decision making part, at least not yet. For those of you non-remote sensors in the room, I have this one slide review of what remote sensing is. Basically, it's an acquisition of information about an object, in this case, an agricultural field, without having a physical contact with that field or object. And there are multiple benefits to doing this from remote sensing, either from airborne or satellite-borne platforms. Because of large area coverage, objective observations, that is, you don't have to rely on a person's views of the field. You simply rely on physical principles, light in this case. Spectral capabilities, ability to see things in different parts of the electromagnetic spectrum, particularly infrared, which matters a lot for us. Wall-to-wall coverage, accurately located in terms of space and time. And then ability to acquire a lot of information in a very short time with a minimum labor input. Now, I also would like to say that when it comes to remote sensing, I think the keyword is spatial, spatial, spatial. If you're interested in a single field, don't do remote sensing. That we would be wasting your money and energy. But if you want to do this over thousands of fields, that's where the cost goes down and the benefits go up. Having said that, there are many, many challenges remain. And in my view, the biggest challenge is this one over here, this mismatch between needs and deliverables. We all want everything at every corner of the field every day. And remote sensing is not able to deliver that. So we got to come up with ways to use the existing observation capabilities to meet the needs that are much bigger than what the observation capabilities can provide. Other challenges are, all of these satellites were designed for multiple purposes. We do everything from forestry to water resources to agriculture. So because of their design, they're not necessarily all for agriculture. So we gotta, do this square peg and a round hole idea that we gotta fit observations to particular needs that we may have. And again, one of the biggest challenges is this inability to determine all variables. We want all those variables, we just can't get them. There might be some cost and processing associated, although that cost and processing is actually coming down really fast because of cloud computing. And lack of subsidies or support, maybe in some places. And I would argue that there's also lack of expertise and capability. There are a lot of tools that are out there, unfortunately, out of reach of many of us because they were designed by a particular person. They're very complicated, and you don't have access to the software to do it. So that becomes the challenging part as well. But maybe those challenges can give us some opportunity. Over the last decade, there has been significant developments in remote sensing arena, mostly in this hardware and the software end, but also in the cloud computing end. So I think one of the nice developments is this big data. Sorry, I said it. I don't like saying big data, but here it is. So there's a lot of big data applications in remote sensing. There are several organizations in Europe, maybe in India, in the US that are doing sort of bulk processing, particularly for agricultural purposes. Almost all with the desire of making more money. That's the end of it. But there might be things that we can learn from those large data processing capabilities and apply them to our own research and application purposes. The other thing is this new image processing tools, particularly merging of environmental sciences and computer sciences. Whenever a student applies to work in my lab, I get this good students with very strong remote sensing capabilities, but they have no programming skills. So it becomes really cumbersome to process large amounts of data without knowing programming. Or I get people with very good programming skills, but they don't know remote sensing. And I'm usually torn on which to hire. And it's difficult for me to find someone with those capabilities, but I think that's where we're heading. I don't think we can do large area processing just by knowing off-the-shelf software like Envy or Imagine. I think we got to push it more than that, and that would be my advice to younger folks in the room. But I think there are also additional algorithms that were originally developed in the computer sciences community, mostly in the computer vision, that are making their ways, finding their ways into remote sensing community, and particularly things like shape recognition. As humans, we're very good at looking at those satellite images and telling where the agricultural fields are. But telling a computer to figure out where agricultural fields are just because of their shapes is extremely difficult. But it seems like we're making some progress with that. There's also large volume methods. Dealing with terabytes of remotely sensed data is just a matter of pressing a few buttons nowadays because of cloud computing. And finally, some automated methods. So just a quick example. Here's a nice agricultural setting. This is a false color composite where red is a healthy agricultural field. And as you can see, we can, as human eye can see these individual fields, we might be able to apply some remote sensing algorithms to figure out and put boundaries around those fields. And it may be possible, I would argue, that if you had the high resolution data, you could do this for the entire country of India and figure out every agricultural field. I think we can do that now. Now, whether that can be used for cadastral applications or individual field yield applications is a different story, but I think we're there. I think we can do these. Anyway, these are some of the things that we can do. And the last thing I'm going to talk about is this idea of machine learning, throwing better classification algorithms, better learning algorithms at classifying or information extraction from remotely sensed data. I think we're making a lot of progress over here, and much of the recent literature in the remote sensing community is trying to use these newer methods for image processing. So with that, I want to talk about 3 examples of agricultural applications of remote sensing. First one is rice mapping in Vietnam. The second one is field scale yield mapping in the US, but I think it can be applied to other places as well. And the third part is estimating evapotranspiration at the field scale using remote sensed data. So let me start with that first one. So as you know, Vietnam is one of the largest rice producers in the world, and that has both political and economic reasons, but it's mostly driven by economic policies of the government of Vietnam. They are just pushing their people, their farmers, to grow more rice, more rice, more rice. In this particular application, what we've done is focused on the Mekong Delta, where it's the rice basket of that country, and then map the locations of rice growing areas, and not only the rice growing areas, but the cycles of rice growing, because there's up to 3 different cycles of rice growing in that part of the world. And this work is done by one of our PhD students, Caitlin. So again, there's a significant push for growing more rice in the Mekong Delta, and this is an individual Landsat. One of the satellites that we work with is a footprint. This is the Mekong Delta, covers 80% of the delta, and that part is located in the southern end of Vietnam. And these are just some of the pictures of rice growing in that part of the world at different parts of the season, different cycles, etc. And I'm showing this just to give you a sense of what the landscape looks like, but I'm also showing you this because rice is a particular crop that spends, at least paddy rice, some of its life cycle in underwater. And it turns out that being underwater and fields being flooded with water has a particular importance when it comes to remote sensing application, because it gives us the opportunity to not only use the green vegetation indices that we're used to using for remote sensing, but also allows us to use water indices from remote sensing just because there is water. And if there is water in that part of the world, there is rice. So all of a sudden, we've doubled the variables that we can work with to figure out where rice is growing and how many times a year it is growing. So with that, we're using 2 vegetation indices. Those of you who are not familiar with vegetation indices, we simply take different colors, in this case red versus infrared, and simply algebraically combine them to come up with an index, and that index becomes, sort of provides much more information than the individual colors themselves. So in this particular case, what we're doing is for the variable called NDWI, normalized difference water index, it's just an index of how much water that is present on a particular pixel or location. We simply use a near infrared information and the shortwave infrared version. And shortwave infrared version simply contains a lot of water-related information. So here's my water index that I can calculate for individual fields. And here is my vegetation index. That's just the amount of vegetation or greenness of vegetation. The higher the index, more biomass, more greenness on the surface. And I can combine those 2 indices to come up with figuring out what the rice looks like on the ground. So it's a three-step process. So first figure out the useful indices. Here they are, and calculate them for every pixel. And then segment the rice paddy fields. What I mean by segment is, as you know, remote sensing comes in these arbitrary units called pixels. And in Landsat sensor, it's a 30 meter by 30 meter box. But that's just an arbitrary engineering unit that no agricultural field confines to, right? Agricultural fields have different sizes and shapes. So we can use some of those segmentation algorithms, that, earlier figure that I showed with the red color, and figure out where the boundaries of agricultural fields are. And usually agricultural fields are much bigger than the individual pixels. So my unit of analysis is no longer a Landsat pixels, which is nothing but a useless unit, but an agricultural field, which is a useful unit that I'm interested in. Because when it comes to agriculture, I'm interested in fields. I'm not interested in pixels, which are, again, just arbitrary units. So that's the second step. And the third step is apply a majority analysis. I mean, I'm making maps at these pixels, but I got to aggregate my pixels into those field levels. And I often use what I call a majority rule to do that upscaling from individual pixels to larger fields. So here's the sort of examples of these steps. So I'm going to take two boxes in this particular Landsat, and this is a true color composite where green is healthy rice growing above the water, towards harvesting, and all the blue areas that you're seeing over here are simply flooded fields, water areas. So what I can do is I can take one of these boxes, let's say take A. This is my original raw data. And I can convert that to a water index. This is what the water index looks like. And I can convert that into a vegetation index. Here's my EVI vegetation index. But not only do I convert it to a vegetation index, but because I have time series of observations, I get an observation every 16 days, I can actually calculate my standard deviation of the temporal stack and the mean of the temporal stack. So that gives me something about the variability of vegetation over time, but also the mean state of vegetation over time. So that's what these are. So here's the NDWI standard deviation. So standard deviation of my water index, standard deviation of my vegetation index. Here's my mean of the vegetation index. And I can combine these into a classification algorithm to figure out those areas that are rice, that are in gray, and those areas that are not rice in white. And as you can see, individual pixels have disappeared because I've converted those into individual field boundaries. So it's just one example from box A. Here's an example from box B. All I'm trying to show over here is that there's a lot of information there, regardless of clouds and other sensor issues. So here's a close-up of that area. So here is, as you can see, that's where the rice is right there. Those are the flooded fields. One snapshot in time. And then I can convert that to that. Those are my individual pixels, but then make a field boundary map. Those were the red boundaries, and then aggregate my individual pixels into those field boundaries using majority rule, and make a map of rice, no rice at the field scale. So those are my individual fields or individual blocks, and then this is just the second example down here. When we do that, we can do that for two different time periods, for 2010 and year 2000 and year 2010. The reason we did that is because we were very interested in expansion of rice in the Mekong Delta. So here's a map that is color-coded to show the gray areas to be continuous rice between 2000 and 2010. Blue areas were rice only in 2010, but not, I'm sorry, in 2000, but not in 2010. And green areas are the places where rice became, landscape became rice only in 2010. As you can see, there's more green than blue over here. It simply tells me that there's expansion of rice growing areas in addition to existing locations. So it is possible for us to make this map for the entire country of Vietnam and Thailand, etc. And here are the accuracies of the maps that we made. As you know, when you make a map, it's just a hypothesis. So what do you do with the hypothesis? You go test it. So we go to the field, we collect their reference data, and then we convert those reference data to what the map told us, and then simply come up with a confusion matrix, which is the sort of metric of analysis over here to tell us how accurate the map is. It turns out that 2000 map, year 2000 map, is about 80% accurate, and 2010 map is a 94% accurate. And the reason the big difference is because in year 2000 we had access to less number of observations than in year 2010. So another lesson that we've learned over here is that those number of observations really matter over the course of the growing season. Now that we made a map of rice, our second step is to figure out how many cycles of rice we are growing, because we had the anecdotal evidence that in year 2000 there was a lot of push for growing 2 rice per year, and by 2010 government was pushing to grow at least 3 at least 2, if not 3 crops per year. And we wanted to quantify how between those years in a decade the rice growing cycles had changed at different locations. For that, we've been using both the vegetation index EVI and wetness index trajectories. I'll show you an example of that in a second. And then to put those trajectories into a machine learning algorithm called a decision tree. Decision tree is simply a decision-making process. You know, if your data looks like this, it goes to A. If it doesn't, it goes to B, et cetera, et cetera. So it's a recursive decision process that humans use every day. And this is what an ideal rice cycle would look like on the ground if I was observing it every day. So a single rice cycle over a 3-year window would look something like this, right? So I would plant it, and I'm growing a single rice in my field. It would grow. It would exceed some vegetation threshold value. That would be my maximum. That's the maximum greenness. Then I would harvest it. The next year I would do the same thing, et cetera, et cetera. Here's an ideal case for 1 year, one rice per year. Here's an ideal case for 2 rice per year. And here's an ideal case for 3 rice per year. This is an ideal case. This is what you see from a remote sensing sensor. Okay? And as you can see, the cycle is incomplete. That's because of clouds, because of other issues. We don't get to see the ground as much as we want. So what we're doing is we're simply working with whatever the data that we can get. So we think that this particular ugly cycle, ugly spaghetti, if you will, is 1 rice cycle. This spaghetti is 2 rice cycles, and this spaghetti is 3 rice cycles. And the reason we say that is because we come up with a threshold based on the decision tree theory that if you exceed your threshold once per year, that's your 1 cycle. If you exceed it twice per year, that's your 2. And if you exceed it 3 times, that's your 3. So regardless of how ugly the cycle may look, in reality, if we can figure out a way to accurately count the number of times you exceed that peak or threshold, that becomes your metric to map rice. Anyway, we applied that to our data and produced these 2 maps. So all the green areas are single crop rice, year 2000, year 2010. All the red areas are double crop, and all the blue areas are triple crop rice. And as you can see, first of all, there's very little single crop rice in the Mekong Delta. It simply doesn't exist. Everybody's growing either 2 or 3 crops per year. The second is in year 2000, there were much more double crop rice than triple crop rice, and by the time 2010 came around, that number actually doubled. The majority of the landscape, up to 60%, 62% of the landscape is actually triple crop. So, and then, so we can produce maps like these and then produce statistics from them. So the conclusion from that particular line of work is that rice paddy extent and management, that is number of growing cycles, can be mapped at sort of field scale or 30 meter using Landsat style observations. Flooded scenes become really important because that gives us just another observation opportunity. So, and this only applies to rice, by the way. It doesn't necessarily apply to upland crops. Rice paddy area in the Mekong Delta expanded only slightly, right? But the area of triple crops nearly doubled in that particular part of the world. Let me switch gears and talk a little bit about yield mapping at the field scale. So one of the things we're trying to do is we're asking this question. I have thousands of fields in my domain, in my study area. Can I come up with a yield estimate for every one of those fields, literally thousands of them? And people have been trying to do yield estimation or remote sensing for over 40 years with some success. And it turns out that many of the studies rely on that sort of evolution of the vegetation index curve. And if you do, take a smooth curve and simply calculate the area under that curve, that's somewhat equivalent to biomass. And with some correction factor, you might be able to convert that biomass into actual yield area. In our approach, what we're doing is we know that remote sensing yield estimate is wrong. We know that a crop model yield estimate is also wrong. But if we can combine the two observations, methods, one the observation remote sensing and one a crop model, a simple crop model, can we actually come up with a yield estimate that is better than individual methods? So some of the parts is actually greater than the sum of the whole variable. So that's what we're trying. Now, in order to do that work, we have to take our satellite observations and turn them into some biophysical variable. Because satellite observations only give us some green index, greenness indicator, but it's not a biophysical indicator. So a biophysical indicator in this case would be something like leaf area index or LAI. So one of the things that we're trying to do, I'm showing over here, is that if you look at the literature, people have been trying to estimate leaf area index from remote sensing for, again, 40 years. And there's probably thousands of publications on this, but if you look at every publication, everybody publishes a different equation. You do work in India, in your particular field, you publish one equation. I do work in my field sites in the US, I publish a different equation. And that is somewhat challenging because if I'm going to expand this over thousands of fields, which equation am I going to use to convert my remote sensing, which is this variable, to a LAI variable, biophysical variable that my crop model requires? So what we're trying to do over here is that I have a graduate student. She took thousands of field observations from different parts of the world, LAI observations, and then she acquired coincident remote sensing observations for those locations. And we had certain criteria that, for example, LAI had to be observed in a large enough field that we can observe it, that the satellite pixel would pick it up. And it had to be a high quality observation, et cetera, et cetera. And once she screened everything else, we ended up with about 1,000 individual field observations paired with remotely sensed data. And the big question that we're trying to ask over there is that since everybody's publishing these different equations, is there a universality to vegetation index and LAI equation? And we're doing that using different vegetation indices. In this case, it's EVI2. It's an EVI without the blue band if you don't have access to blue color, and the leaf area index. And these are the sort of different locations, and this is the confidence interval over here. And let me show you some locations. Those are the locations from which the LAI data comes from. So let me make my pitch over here and tell you that if you have any LAI observations in ICRISAT, I would love to get my hands on it. So those of you who are field folks making crop-specific LAI observations, I would love to have access to them just to be able to improve this particular study. As you can see, there are no observations from India. And we would love to put a data point there. But anyway, so we take those observations. We have about 1,500 data points, and then come up with a relationship. This is a big soup of statistical analysis. And if you combine all the crops together, regardless of which crops it was observed, this is the kind of relationship that you would get using one vegetation index against that biophysical variable, and this is the probability density function of your predictions. And if you do it by crop type, in this case maize, your relationship becomes better. So we learned two things from this particular analysis. There seems to be some universality to this EVI or vegetation index and LAI relationship, but it's a messy. And if you divide it, if you sort of parse it by crop, you do better, wheat versus maize. What that means is you got to know what your crop is if you're going to do this sort of yield application. Now, again, the only reason we're doing all of this is because our crop model wants an LAI in it. So I got to convert my remotely sensed observations to LAI. And if I can sort of quantify that relationship and make it universal, I can take every one of my EVI, vegetation index, remotely sensed observations and turn them into a biophysical variable then that I can plug So the next step, once we figure out this sort of LAI messy part, and these are the equations. These are all being published, so I'm happy to share those with you if you're interested. This is just another way of validating how well the model is doing. So out of sight, out, et cetera, et cetera. But this is just a part of the statistical analysis. And one of the things we can do is take those EVI LAI relationship and make maps of LAI. This is very powerful because if this is an agricultural field, that's an LAI map of the agricultural field. So it gets into this idea of precision agriculture if you're interested in understanding within field and field variability. And the three pictures that I'm showing over here are simply different scales. Here's a field scale. Here's a regional scale from Landsat, where you can see individual fields, but not necessarily within field variability. And here is a sort of a large area for the entire state of Iowa. And the whole purpose over here is that the relationships that I showed you, they hold across spatial scales, whether it's field scale or state or regional scale. So our next step is we get forcing data. Forcing simply means weather data, daily weather data, because our model requires that. All agricultural models, crop models require weather inputs. Then we take remote sensing observations. And then we come up with a gridded crop model. And then we do a simulation. When we do a simulation, the model gives us LAI, a predicted LAI. It also gives us yield. And then we take the data assimilation approach where we ingest remote distance observations whenever they are available. So imagine that you're running your model started running today, and it moves forward every day, tomorrow, the next day, and makes predictions of LAI. And on the third day, we have an LAI observation from remote sensing. What we can do is we can compare the LAI observation from remote sensing to the predicted one from the model, and then come up with an intelligent way of which one do you trust more? Do you trust the model or do you trust the observation? And that's where this sort of data assimilation comes in. And the tools that we're using for data assimilation actually comes from meteorological modeling. So atmospheric scientists do this a lot. They have a weather model. They're trying to project into the future, and they do a course correction in their weather model by ingesting high resolution remote distance observation. We're doing the same thing, but we're doing it for crops, for LAI. Now that we converted our vegetation index into LAI. So we're doing data assimilation. So update simply means I update my predicted LAI, and hopefully it's a better prediction now. Now model moves forward, makes other predictions, evolves, and then on the third day, the fifth day, I make another assimilation, do a course correction, and do course correction until I predict the yield at the end of the growing season. Now, in order to do this, you could do this with a very complicated model like DSAT, highly parameterized model, or you can do it with a simple model. In this case, we chose to do it with a simple model, simple light use efficiency model, simply because we didn't have enough computing resources to parameterize the particular model over here. Once we do this, it gives us 30-meter resolution or field scale resolution yield map. So that's just a distribution of yield across a gradient. Here's a histogram distribution. And then we get LAI maps, but not only that, but we also get soil moisture maps as a byproduct, which I'll show you in a few minutes. This is the same figure, same strategy. So here is the forcing data. Here is the crop gap filling segmentation, bring in LAI time series, do the ensemble common filter data assimilation, come up with some predicted LAI, and then bring that into a crop model, and then come up with a yield map at the end of the growing season. So these are some of the results from this exercise. These are results for one particular field. In this case, the red line over here, dashed line, is an open loop version. Open loop simply means you do no data assimilation. Let the model run all by itself based on the weather parameters and some coefficients of the crops. And the blue line over here is the assimilated version. That is, you make a course correction every time you have the LAI observation. And the reason this is jumping up and down over here is because the data assimilation is saying, well, your area predicted LAI is just too low, because remote sensing says it's got to be 10% higher, so you simply push it up. It is possible to fix these are called errors actually. It is possible to fix these little jumps by simply improving the frequency of observations of LAI. In this case, we only had I don't know, a handful of LAI observations. But if you do it from satellite, and if you actually fill the gaps in the satellite data, you may be able to do this every 5 days, every 2 days, whenever the satellite data is available, barring clouds and other issues. So that's the LAI part. Here is the biomass part. So here is the open loop version. That's what the model would have produced in terms of biomass. And here is what the model is producing in terms of biomass with the data assimilation. And simply open circles over here are the observations of biomass. Again, if there are biomass continuous time series biomass observations around the fields over here, I would love to work with those data simply to test these ideas in different parts of the world. So I think ICRISAT, I mean, I've seen those fields in the campus over here. Some of those fields are really well positioned to test some of these ideas here in this part of the world. That's the biomass part, and biomass is somewhat equivalent to yield. And this is the soil moisture part. So the nice thing about this is that there are soil moisture products from satellite data, as you know, and you may be using them. But the problem is that they're really coarse scale because they're microwave data. And passive microwave gives you these really big pixels, like 30-kilometer pixels, which are somewhat useless for agricultural applications when it comes to field level applications. So a byproduct of this is that because of data assimilation process, we have the ability to downscale those 30-kilometer pixels down to individual fields just because of the assimilation process. And simply what it's doing is, here is my big soil moisture pixel, 30-kilometer, and here's my individual field. But because I know what my individual field is doing in terms of its green biomass going up and down, I can actually adjust my soil moisture, big pixel, into what the variability in my individual agricultural field is. And this is what the results look like in terms of data assimilation. So here is the open loop version right there, no data assimilation. Here is the open data assimilation, the green one, doing data assimilation of only vegetation index from remote sensing. And the red one is doing data assimilation, both soil moisture from satellite as well as vegetation index from satellite. And as you can see, the best root mean square error comes from when you assimilate both the soil moisture and vegetation index. And these are the types of products that you could generate from this. So here is a maize soybean crop type map for a particular year. This is for a particular state of Iowa. This is the LAI map that you would generate by using that statistical analysis that I told you earlier. Here is the soil moisture map for every field, and here is the yield map for every field. So again, I'm just showing you that there's possibility over here. These are the things that I think we can do. And finally, the soil moisture assimilation result. So here is that big pixel, and here are my individual fields. That's one individual field. And because of the data assimilation process, I can take this and simply disaggregate my big soil moisture pixels into these individual pixels, and then show that there is a nice correspondence between observed and predicted soil moisture data. And then now this is a predicted product, but if this product is good, then you can do all sorts of things about drought and water use in the soil column, et cetera, et cetera. So it may be possible to use that residual soil moisture in the soil reservoir to do some additional analysis. Let me switch gears and talk about the ET part, evapotranspiration part. And this time I'm going to take you to the Middle East, because that's where most of the irrigated, well, no, India has the most irrigated lands. So just to bring everybody on the same page, the word of evaporation is simply vaporization of water. And the take-home message from this particular slide is that vaporization or evaporation or evapotranspiration takes a lot of energy. It requires a lot of energy. So many of the methods that are trying to get at this evapotranspiration variable use what's called an energy budget equation. We simply do an energy budget using the observations that are provided by satellites to us. Evaporation is the part that is coming from the soil, and transpiration is the part that is coming from the plants, but we usually can't separate them, so we simply merge the terms and we call them evapotranspiration. Now, when it comes to irrigation performance improvements, the whole idea, in my view, is decrease E and increase T. That's how I look at it. That's what makes sense to me. Again, it's very difficult to distinguish E from T often, and different times of the year there's going to be more E if your crops are little, they're not taking up so much water, etc. So this is what usually looks like. So if you have an LAI curve, right there, it's just an ideal hypothetical curve. Your ET, or soil evaporation, would dramatically decrease in times when your LAI is maximum, because you're extracting maximum amount of water from the field. And this has all sorts of applications for irrigation management, et cetera, et cetera. There are a number of variables that derive how much ET would occur from an agricultural field. I sort of divide them into two categories. The atmospheric part, that's the demand part. How dry, how ventilating my atmosphere is, and how much demand do I have. And then there's the surface part. How much water do I have to satisfy the demand? That's where the irrigation comes in. And also the vegetation type. Again, the higher biomass, the larger transpiration I'm going to suck out of that soil. When it comes to remote sensing, there's usually sort of two categories of getting at ET. The first category is what's called a vegetation index approach. So it's actually very similar to the crop coefficient approach that you may be familiar with. You calculate potential ET. Instead of using those published ideal crop coefficients from FAO, you simply replace those curves with your vegetation index curves. Because those vegetation index curves, if I show you an ideal curve, look just like those crop coefficients. But they are observed rather than hypothetical or idealized. So that's one way of getting at that ET variable. Another way of doing it is this energy budget approach. And this energy budget approach, it's a stronger approach. It's a more complicated approach. And it has a limitation of having access to thermal data. If you don't have any thermal observations, heat observations, you can't do this. So that, it's usually a higher accurate, but a more involved part. So I'm going to show you some examples of that. In terms of surface energy balance, we use a simple equation called surface energy budget equation. The surface energy budget equation simply tells us that I have some radiation coming from the sun, and I correct it for reflection factors, etc. And I have certain units of energy available to me. Let's call it 100 units. And I can do three things with that 100 units of energy. I can evaporate water, I can heat the ground, or I can heat the air above the ground. And the evaporating water is the one that I'm interested in. So what we often do with respect to the energy budget equation is that we take that equation and simply rearrange it. And then we put LE, which is another term for evapotranspiration, and then we simply get it evapotranspiration from all the other variables. So it turns out that we know this variable, we can measure it, both from satellites or from ground observations. We often make estimates of ground heat flux, that's the amount of heat that would be heating below the ground. So the biggest unknown at the end of the day is this H variable, that's heating of the air slightly above the surface. And that's a variable that has two important components or predictors. The first predictor is how hot at the actual surfaces, that is, if these are my crops, if I put my hand on the crop, how hot are they, how cool are they? And how cool or hot the air above my crop, 1 meter above, 2 meters, 5 meter, 100 meter, et cetera, et cetera. Because if I know those two variables, I can write the equation of flux, and as you can see, as you know, flux is about gradients. So if this temperature is 10 degrees, if this temperature is 20 degrees, I'm going to use 10 degree gradient, and I can convert that to a flux equation, and H is nothing but a flux variable. So it turns out that if you have thermal observations, right, so you can get at the surface temperature part. So satellites will give you for every field, every pixel, how cold or hot your surface is. And what you don't know is the air above the field. If you have a meteorological observation in your field, you're done. You can go home because you're making the measurement of air temperature. But who has observations for every field if you're doing this for thousands of fields? So that's where the limitation is. So there are different ways of solving this H part. Some people assume that I can look at a landscape and I can figure out where my hot locations are and where my cold locations are, and come up with a gradient on the surface and simply replicate that gradient in the air. That's what the C-ball is doing, if you're familiar with that term. Another term is to solve that H iteratively. Come up with some arbitrary values of that variables that go into H, and draw those values from a probability distribution, known probability distribution, and simply solve that equation thousands of times until you get a convergence. And that's the approach that we've developed, or one of our students developed. So it's called the HR-MET approach, so high resolution mapping of evapotranspiration, and it's an iterative solution to the H that starts with arbitrary values of inputs and assume known uncertainty probability distribution. So the nice thing is that instead of making one ET map, you make thousands of ET maps for every iteration, and then you simply report the means and standard deviations from that. It's computationally expensive, but with today's computers with large number of processors, it's actually not that bad. So here's the approach. So you take some meteorological data, kind of surface temperature from satellites or airborne platform, some vegetation index just to figure out how your vegetation is, how high your vegetation is, and then do an iterative solution to this part to come up with an ET as an output. Let me show some examples. Let me skip that. So one example in Morocco, there's a particular irrigated perimeter called Douala region in the sort of center part of the country. It's a World Bank GEF project where we applied this, and fields are cultivated with sugar beets, potatoes, and cereals, and several fields are equipped with soil moisture and flux for water balance calculations, and this becomes our sort of validation data point. And again, if there are validation data points here in ICRISAT, particularly calculated from either closed water budget analysis or from other means, I would love to look at those data and have access to them so that we can test it over here. This is what that irrigated perimeter looks like. Individual fields are individual crop types. Those are all field mapped, not from remote sensing. So those are the individual meteorological stations. So here's an example of one corner of the Douala region. So in this case, I'm showing first NDVI, just another vegetation index. Green means high biomass, high green, and yellow means no vegetation. And here's the ET equivalent converted to millimeters per day variable. As you can see, there's a very strong correlation. This is an irrigated field over here. There's a strong correlation between how much vegetation you have in the field and how much ET you might be getting, up to 5-6 millimeters on that location. But the nice thing over here is that for every field, we get an ET value. And then one of the nice things about this approach is that if I know the yield at the end of the season for that particular field, and if I can keep track of the ET that field is losing, then that opens the door for me to get at this water productivity variable that most of us are interested in. How much water do I have to sink into my field to get at the yields that I'm interested in? Here's another example, different location. Another example, different location. And here's the sort of time series estimate. So the blue one is the estimate from remote sensing. The red one is from observations. Now, you may wonder, well, how do you get a continuous observation like that? Because remote sensing doesn't give you the continuous observations. I get data at best every 8 days. So this observations should be punctuated. The way that we get around that problem is that there is a very strong relationship between the potential ET or solar radiation and evapotranspiration. So what we're doing is we're simply infilling between the observation dates using potential evapotranspiration as a proxy. So that's what the gap filling is coming from. So that's an example from that part of the world. And then we've done the same thing for parts of Nile Delta. So here's the delta right there, and then here's the ET map of that particular area. Crop fields are slightly smaller over here. I would love to be able to apply methods like this in places in India, especially in places where irrigation is important and groundwater decline is important, and come up with sort of quantitative estimates of how much demand is coming out of those fields. So those, there will be some really interesting applications. And these are the time series ET maps. So the redder is less ET, bluer is more ET. So that's for February, there's March, et cetera. So we can actually come up with some time series estimates of different locations. So in terms of, oh, sorry about that. I have to do it again. So I think I already talked about this. In terms of ET conclusions, remote sensing of ET is possible with reliable accuracy and sufficient spatial resolution. I think we can do this. Energy balance approach is probably the way to go, but I think there's room for the vegetation index approach as well. And it turns out that the error rate is about 15% for a particular date for a particular field. So that's the error. I mean, and I would say that's probably the best error or the average error. So that's the error that you have to live with if you're going to deploy this over large areas. And accurate air temperature seems to be one of the most important variables that you have to get at. So getting at that sort of high resolution, if you have it, air temperature is important. So I'll stop there and take questions if you have any. Please go ahead.
This soil moisture from, are you able to hear?
Yes, I can hear you.
Yeah, the soil moisture from a very coarse resolution of a quarter degree is currently available that you have brought down to the field level. See, there are many downscaling algorithms have been reported in the journals like universal triangle approach, where the soil moisture and its relationship by taking the various data like albedo, temperature, and then NDVI and these kind of things. But whereas you have shown a very simplified approach, even that universal triangle approach, it could not effectively downscale the soil moisture to the field scale because a lot of unable to explain the complete variability of the moisture at the field scale. But you have shown a very simplified approach. I really wonder whether it works.
Well, I showed some validation results. So as far as those validation results are concerned, it seems to be working, but it's not a universal validation. So I would love to test it in another location and see. And I wouldn't necessarily call it simple, to be honest. Basically, what we're doing is we have some dynamic vegetation, and this dynamic vegetation model has some soil bucket, soil component, soil water model in it, and it's simply saying that if your vegetation is doing this, your soil, you can downscale your soil from those big pixels into those small pixels. That's the approach, but I wouldn't call it simple.
In farmers' fields, say, for example, Vietnam rice farmers' fields, the greenness is not only because of the crop, but also because of the weeds. Can you differentiate?
Because of what?
Weeds, unwanted plants.
Oh, I see.
Can you differentiate between the crop and weeds, and can you calculate the vegetation index of the crop and the vegetation index of the weeds?
No. No, we can. Yeah. I mean, this approach often breaks down in places with significant weed problems or pest problems, although we might be able to get at reduction in biomass because of pests. But weeds are very difficult.
You have shown in Vietnam where the entire area is grown with rice, but you come to this area, Telangana region where there are many crops are there. So even we are seeing our colleague also generated some maize map. So we are finding very difficult each field with the other crop also. Do you think it is easy to remote sensing to identify all the crops?
Well, crop type mapping itself is a difficult problem. Yesterday I was visiting the remote sensing center, and one of the questions I asked them is, I've done crop mapping in different parts of the world, and I find India to be most challenging because of the reasons I just described. But at the same time, I think it is possible because they're doing it. They're doing it very successfully. There are other organizations in India that are doing it. If you're growing 3 crops in a plot that is as big as this room, I'm pretty sure that you're not going to be able to do it. But the question is that the norm or is that the exception? I don't know. It could be. Please, yeah.
It was a good presentation by you.
Thank you.
3 presentations you clubbed into one, and it's very nice. Only one or small 2 doubts which we share with you. This passive microwave radiometry, what you are referring to, is a very big footprint. There is one more associated problem. At such high frequencies, when the LAI crosses something like around 2 to 3 units, then there is attenuation. But the soil moisture requirement is there throughout the cropping period, and more so in the periods coinciding with the flowering, etc. signal itself is contaminated.
Right. So if I read it correctly, most of the microwave attenuation because of vegetation occurs in really high biomass areas. And crop biomass, usually there might be some pollution in the signal there, but I'm talking about tropical forest type of pollution, not necessarily agricultural biomass pollution. At least that's what I've read. The second is I take soil moisture data at face value because I'm not a microwave remote sensing person. I'm simply saying that if there is an existing soil moisture data available every day to me, even at the coarse scale, let me try to assimilate it into my yield approach. And there seems to be some improvement, although marginal improvement, in my yield prediction. And that soil moisture downscaling is just a byproduct. I don't have to do that part, but I could do it.
The only point is you're right to certain extent what your observations are. But when even the crop plants also, that high frequencies, 90 gigahertz when they are using, attenuation is bound to be there. Even once it crosses 37 gigahertz itself, the attenuation is so high. It has been recommended to use this microwave radiometry in the early part of the early season of the crop, up to something like tillering phase in case of monocot crops, or during the latter stage of the crop when the crop starts senescing. At those places, it provides a good. And what I would also like to know is, is it taking into account the phenological variations that are occurring? Whether it is LAI retrieval, or whether it is soil moisture retrieval, or even the yield map for that matter.
The only phenological information that is coming in is from remote sensing. So we take the vegetation index from remote sensing, convert it to LAI, biomass, biophysical variable, and we simply do that at every observation, if there's an observation, because of clouds and other issues. So that's how we capture that phenology. If there's an observation, it's in there. And going back to your first question, I don't doubt that the attenuation is there. But again, I have to take the soil moisture data at face value. And you know, there's a SNAP sensor that newly launched, and they're producing, I think, soil moisture, high quality soil moisture data sets. But again, I have to trust the quality of the soil moisture data. And I don't use the microwave directly. I use the soil moisture end product in our research.
And if I just may reflect on one of the questions asked by the colleagues, using remote sensing crop type discrimination has to be differentiated from crop mapping. You may be having a capability to discriminate different crops, but you may not be having a capability to upscale it for larger area mapping. Because when you are considering larger areas with heterogeneity, so many other factors also have to be accounted for. So as far as India is concerned, for mapping, we have identified 8 crops, as yesterday we were telling you. For 8 major crops of the country, we are in a position to map it. Discrimination is possible between, sir was asking about weed and crop. That also discrimination is possible. In remote sensing parlance, there are differences between identification, detection, discrimination, classification, and mapping. These are 5 different terms which are to be used at different levels. So discrimination may be there, but mapping is not such an easy task. It requires a little different. I think he also agrees for it. And my last question to you is with regard to the ET estimations. ET estimations are also very phenology dependent. So is the phenology entering into your part? That is one. Just let me complete with the second part. Because ET observations, to compare it, if you are having a point observations only possible. Otherwise you need to have large aperture kilometers set of things. Have you used any such thing, and what is your experience on that?
We use flux towers that are installed in individual fields to do the validation.
But that is a point observation.
It is, yeah.
Whereas ET, once you are talking from satellite parlance, it is an aerial observation.
Absolutely.
So
a scintillometer would be a great way of doing that. You don't have access to scintillometer. I haven't tried it, but that's probably another way of testing how well this is doing.
We have one large aperture scintillometer with our center.
Okay. Is it over an agricultural field?
Yeah, it will put it on that one. Okay. And in one season we could partition that. RN, GH, lambda E, all the 4 we could partition it. But only problem is the evapotranspiration doesn't end with energy balance alone. Of course, there are issues with energy closure as well. But at the same time, what we are looking for is there is advection, which is also causing a lot of heating. That is not accounted by our radiation energy balance method. So for that, we need to supplement it with something else. But unfortunately, our scintillometer is now out of order because there was some small problem with the instrumentation, which we are likely to get it repaired this time. So next time, I think for the next forthcoming monsoon season, we may be able to have the data, which we would like to analyze and then share with the people. Thank you.
I think it would be great to apply a method like this over a number of fields for which you have the scintillometer transits, and then compare them. I would love to do something like that. Absolutely. Yeah. Go ahead.
After this season is over, before this monsoon season commences somewhere in June or so, we'll be in a position to keep the equipment in order. And then we'll get the data expected by the end of this year. You can see throughout the philology how it is varying. Thank you.
I was surprised to see your LAI vegetative index relationship, and the fact that at LAI below 2, you still have very, very loose relationships. So why is that? You would expect normally that the vegetative index would give you very close relationship. Well, maybe not at high LAI, but LAI below 2 normally you should have. So what is the resolution on your maps? 30 meters. So the biggest reason in there is if you look at our paper, we're not only comparing crop-specific LAI, but also different methods of measuring LAI. There's probably half a dozen different ways of measuring LAI in the field. Destructive methods, you go to the field, you cut the leaves, etc. Optical methods, etc. And it turns out that even if you subdivide it by a method of observation, then your relationship becomes strong. So if you look at many of the publications in the literature, they show these beautiful relationships, almost sort of R square of 0.9, 0.8 between a vegetation index and LAI. And if you look at the study, it's done in a particular field, very sort of pedicure conditions, if you will, highly controlled environment. And you look at that publication and you say, well, I need an LAI map for my crop modeling. Can I take that equation and apply it? And it breaks down completely. So what we're doing over here is that we're sacrificing the quality of the relationship by universality, applying over larger areas. So the maize relationship that I showed you, it's actually maize combined from all over the world. So that's where the error is. That's where the spread is in the data. Different locations, different measuring methods, etc., etc. Because I'm trying to keep that universality part my main focus. Otherwise, I can't really apply this in different locations. If you had some slightly higher resolution, let's say you have an extreme which is like super high resolution, and then your case is pretty low. There on the middle point, variation because of your LAI, your range, and then you use position in such a large resolution. So where to fix the resolution of your vegetative indices? There's always room to improve. And we have satellites at 50 centimeter resolution. That'll give you vegetation index at 50 centimeters. The problem is you won't get the temporal dimension because they're what I call composite stem images. You get one area one time and you move on. Landsat is the best compromise. You get every location and you get them very frequently. But you get that kind of relationship. I see your point. Yeah. So, but this is what we have.
Can I ask one more thing?
There was a question in the back. Do you mind?
As I understood, to estimate yield, and you need some empirical relation of LI and EVI, and then some relation of LI and biomass with yield. And you spoke about global relationships. My question is in general that how much can we trust on this empirical relation in
future as this empirical equation and relation will be and can be changed during the time?
I'm not sure about whether the LAI-VI relationship is time dependent, meaning if I do this study 10 years ago, if I make observations in 10 years ago, I think those observations would still hold today because there isn't anything inherent about vegetation that should change the relationship because of time. Having said that, going to different locations will change the relationship because the way you grow the crop and the variety of the crop that you're growing, in particular maize, for example, will be different between locations. So that relationship will change, and that's why you see that big spread in the data, the error in the data. But that's the first time, believe it or not, anybody has tried to quantify this universality of the relationship. Otherwise, if you want to do this study, what you have to do is you have to go to the field, you have to make your LAI measurements in that field, and then come up with your better relationships, and then apply them, and they'll be perfect for that field. But that's not remote sensing. If you want to do remote sensing, if you want to expand it to next 100 fields around you, then you don't have opportunity or the resources to make 100 additional LAI measurements. Hence, you got to let go the accuracy in the relationship. That's the approach that I'm taking with these. Does that make sense?
But I mean, I see Elias' point. The point he's making is when we use crop models also, we use, for example, a relationship between the leaf number on the leaf plant at a certain stage and the area. That's what we use to characterize the genotype. That's more or less the area we should have. So that's where we really need the accurate measurement. But of course, it takes time and you are looking for ways to go quicker to measure those areas from the start.
My sense is if you wanna get at maize LAI around different parts of the world, the relationships that I showed is probably the best you can do, unless you improve your spatial resolution, add more observations into the statistical relationship to concentrate the relationship. But that's, I think, the best you can do. That's if you know the crop type. You gotta know the crop type. If you don't know the crop type, then you gotta use even the verse equation, that is the global equation, which is work. That's just the nature of things, unfortunately. One thing I forgot to mention, hang on one second. One thing I forgot to mention is there may be a possibility, and I've been toying with this idea, to use crop models like Assimilation or ICRISAT to generate LAI data. Not only just one realization, but multiple realizations of LAI with different weather, with different coefficient parameters. And then try to bring that in as an additional constraint. For example, if I'm working in this area, my sort of global LAI-VI relationship tells me that the relationship is like this, but I have this additional resource, right, that has been given to me by some sophisticated crop model. Can I improve my relationship and then use that in my further sort of field scale analysis? And the other thing I want to mention over here is that our purpose over here is to do field level yield data. There have been thousands of publications that do sort of large area yield estimation from remote sensing. They're being done every day. We're trying to get a field level. And when you go to field level, then you got to have field level AI. There's no other way around it. There might be ways to better concentrate or characterize the sort of, let's say, error in the AI based on some crop model input. I think there might be room there's some room for that. Are we out of time or? Please, yeah.
Index, biomass, soil moisture, they are the biggest challenges for the remote sensing community. And especially what we would like to know is when you are taking data from throughout the globe on maize leakage index, what type of atmospheric corrections you are doing to the reflectance? Are you applying anything or do you recommend any correction?
Those are all surface resistance data. If you using the LAI-VI algorithm that was specifically designed for Landsat data at NASA. So, and all data, all image data from this algorithm. If you do actually the other part of our paper is that what if you don't do atmospheric correction? You don't get any of that. So two lessons is you gotta do the atmospheric correction. You gotta convert your surface data to surface reflectance at minimum. And then crop-specific relationships seem to be better than non-crop specific. Those are the sort of two lessons that we take away from it.
Atmospheric correction, which method do you
LEDAPS, L-E-D-A-P-S. I can send you the software if you want.
Okay, we'll try this.
Yeah, absolutely. It's public software. Yeah.
6S code and others are quite complicated.
Well, LEDAPS uses 6S actually. Yeah, iteratively. Yeah, it's getting it from a global reanalysis program.
With respect to your rice mapping, how many overpass dates you have used in mapping rice? That is one point. How do you account for the staggering in the planting time? Because all entire rice area is not planted at the same time. There is a staggering, and how many days you have used. The other important thing is that you have used NDWI, which operates at 1.55 microns, but the research has reported that the use of NDWI, sphere band at 2.1 nanometers, at 2100 nanometers, that is what we call LSWI, it has higher dynamic range and more sensitivity than NDWI. So why did you use NDWI? So the first thing is how many dates you have used for rice mapping, how did you account for staggering, and what is the reason for using NDWI rather than more sensitive LSWI?
First question, we can go back to the figures that I showed you. Those were for one field, but for every field, the number of observations are different. Because there might be a cloud here, there might be a SLC off gas here, etc. So I think the total number of observations range from 16 to 35 over the course of the growing season, over the course of the year. But it's different for every field because of cloud issues. But we can go back to the counting. The second is the staggering. So there's no staggering within an individual field. There's staggering across fields, across the region, but this analysis is done at the individual field level. And the way that we do it is we simply count the number of peaks. And rice on average for triple crop is about 100 days in Delta. So you simply count, within that 100 days, do you get an observation that exceeds your threshold? Now, it is possible that on a day when you should have exceeded the threshold, there was a cloud for that field, and you don't see the observation, right? You don't get to see that peak. In that case, it's a false classification, because you just don't get to see the landscape. But the nice thing about it is that we call it the brute force approach. We take all the observations, download them all, and throw them all at the classification. And the third is, the reason we're not using it is because it's about peak counting. So whether you have a more sensitive or less sensitive water index, as long as you exceed a threshold, the differences are so small that they don't push you above the threshold or below the threshold. Thank you.